related questions. And I also want to say that she also spends a lot of her time on a mathematical project called Gaussian retribution. Is that correct? So you can ask her about that afterwards. And take it away.
Anyway, hello. So I'm going to be talking about language acquisition and language models, as you might guess from the title. But we've been talking a lot about language models modeling specific things. We think of them sometimes as general reasoning engines these days. So why are we going to talk about language specifically? Well, why are they so good at learning? Like, we've had these enormous explosions in performance. It's because language evolved to be learned. Why are they so good at reasoning compositionally? Because language is compositional. Why are they able to accurately answer a bunch of questions about the world, maybe even suggesting that they have internal world models? Because language compresses all of the things we care about in the world. I mean, that's a very, very big statement. Maybe not 100% everything everyone here cares about, but by and large, as a species, if we care about, say, specific dog breeds, then we're going to put it in ImageNet as a label. But if we care about specific pigeon lineages, we would have put them in ImageNet as a label, right? So every single task that we've really focused on most of the history of machine learning is secretly kind of multimodal, because language is how we express the things we care about. Okay. And also, why are language models so useful? It's because language is an intrinsically cooperative modality. Just to emphasize this a little more, just going to compare vision, something that we as a species rely on pretty heavily with language. This is a CFR 100 wolf. I can kind of tell it's a wolf. It's 3,000 bytes. And then 4 bytes, I am very comfortable saying that is wolf, right? Visual cortex, it's had so much time to fix our hallucinations, optical illusions, selective attention, and all of the blind spot issues. It hasn't, right? Broca's area, which we use to generate language, it's less than 2 million years old. It's enabled the entirety of civilization, right? Okay, and for images, I'm trying to generate images. I will not, because actually I'm quite bad at that. And people go to school for years just to learn that. Can't rotate a cube in my head, though that's a me thing. But whereas language, I use it constantly internally, and I am generating it as I speak. And finally, cooperative elements. Photons do not care if you can tell what they are bouncing off of, whereas language co-evolved with all of the other humans that we talk to in order to enable that understanding. And those humans will cooperate specifically to try to communicate clearly, while vision is full of some adversarial elements like frogs trying to camouflage. Okay, so this is my pitch for language as a modality. You've had your hand up for a while.
Don't know English, I would still be able to tell that's a word.
That's true.
And I
sure.
Use my visual cortex in order to decode that's written in English as well.
Yes, but also if I just said the word wolf, you'd be able to decipher it.
No English.
You could also, sure. I mean, yes, you have to know English, but also that's like part of how we've developed, right? Is that we have developed a compression system, but part of the compression system is you have to have the agent actually represent the decompression or the reconstruction. Yeah.
So what do you mean by generation here? And how much of this is that I have a mouth I can speak, whereas I don't have a little screen on my hand that can explain?
I mean, Broca's area is used for both speaking and writing. So if you only spoke sign language, you would still be using Broca's area for it.
Right, I'm talking about an image case, what would it like? You know, I can generate an image if I draw it, but you're clearly demanding some standard of fidelity to some distribution or something.
Yeah, I would say that the fluency with which I generate language is able to match the desire I have to communicate what I'm thinking, whereas the fidelity of an image that I would produce by drawing would definitely not represent that fidelity to what I intended to communicate, because I'm bad at it. Also, I mean, for me specifically, I'm particularly bad at it, but for anyone here who hasn't had training, they probably wouldn't fully be able to convey exactly what they wanted. I mean, maybe you could draw a wolf, but probably in all likelihood, it would look the same as a dog. But anyway, moving on from my pitch for the language modality, which I think is maybe not so necessary because we've all sort of seen what language models have been accomplishing recently. I'm just taking the position that if you want to understand language models, you have to think about language. And specifically, if you want to understand how they learn, you should be thinking about how they learn language. All right, so I'm just gonna go over this real quick, breakthroughs. Yeah?
Language, you mean natural language or language in the sense of more broad?
What are you thinking of as an unnatural language?
Formal languages.
Oh, formal languages. I mean, yeah, we have like highly specialized sort of languages that we've developed for specific things. I think we could sort of talk about formalism. I don't have a commitment on whether I'm classifying that in the same category. That certainly isn't part of the stuff that we learned really easily growing up. But all right, I'm just going to talk quickly about unpredictable breakthroughs. We've already sort of gotten an overview of this from Misha, but basically, you know, you can have these breakthroughs during training, like big phase transition. It could be happening at the very beginning of training when we sort of select a basin and start moving in a consistent direction instead of oscillating wildly. It could happen during the formation of induction heads. That's a pretty famous case. There's grokking, which, you know, that's memorization to generalization. There's hierarchical generalization, which I will be talking about later. And then there's also breakthroughs in scale, you know, emergence. MMLU suddenly is solvable at like specific scales, right? It's these kinds of capabilities that are nowhere and then they're somewhere, right? It might just be a thresholding artifact, but maybe we'll talk about that later. Okay, so what makes a capability a breakthrough capability broadly? I'm just going to say that I think it's compositionality. It's a competition between possible solutions that are valid within the distribution of the data. And multimodality, not in the sense of adding images, but in the sense of a distribution that has multiple modes on it. And I'm going to pose a bonus question, which maybe I won't be able to fully answer, which is, are these all actually the same thing? Well, I'm going to start by talking about sudden syntax acquisition in masked language models. And I am later going to be talking about some completely new results. This is going to be the only part where I'm talking about stuff that I've published already. So in this case, we're talking about masked language models, which is not everyone's favorite language model right now, but it's basically just predicting a masked out token instead of causal language models or autoregressive language models that predict the next token. So for this kind of random masking schedule, you can build your pre-trained model, fine-tune it for other tasks. You've probably had some acquaintance with them, even if you've only been looking at language models since the big GPT explosions, but you've probably at least heard of BERT. So there's an observation that's been made already long ago, 2019, which is that some of these attention heads attend to specific syntactic relations or sets of syntactic relations. So let's say this is your subject head, then it'll attend to the subject of your target token. This is a naturally emerging property. It just shows up during MLM training, at least in BERT. And we're going to be measuring it with unlabeled detachment score. Anytime UAS shows up, it's just measuring how consistent this parsing behavior is. Okay. So we know that they have these syntactic heads, but we don't necessarily know that they're actually important for grammatical understanding, for representing language effectively. We have just instance level observations, which are inherently correlational, that this does develop. There are specialized heads that have this behavior. And then we also do know that removing them hurts the model's performance, but there's, well, this is correlational, could be some kind of side effect of training, could be something that's sort of unrelated, might not be actually necessary. And this is causal, but also there's multiple reasons why you might damage performance by removing a head. It could be entangled in particular ways. It might not be about the actual grammatical information. So let's find some actual evidence a little more for that. One thing is just to ask, when does it emerge? And to look at what happens after. So it's acquired very suddenly. This is the point where the syntactic attention structure pops up, and you can see it's very sudden. And let's call this bit at the end of that stage, because it pretty much plateaus, maybe even declines. It happens during a huge drop in loss, so clearly it's important. And very interestingly, this bit at the end, after you've acquired it, is when you start being able to handle really complex linguistic phenomena as measured by BLIMP. This is a data set that asks things like, well, in most dialects of English, you would not be able to say, I go to the movies anymore. You can only say, I don't go to the movies anymore. So this is what's called a negative index scope. So you need to be able to see what the scope is that you're in order to actually, there we go, negative polarity indexing, word. So this is something where you really do have to think about the hierarchical structure of syntax in order to solve a problem like that. That's just one example. There's a bunch of these. Okay, so I'm going to call that compositional. We can talk about compositionality later if we have time. But I'm going to say, okay, this is a big breakthrough and it's something that's compositional. It has this latent structure that's being learned and depended on. This is the unlabeled attachment score, which is like parse accuracy of this. It's basically measuring the like specialized syntactic heads themselves and how much they are actually pointing to specific syntactic relations. So every time UAS comes up, it means it's a measurement of SAS. So you can just remember it that way. All right. So what happens if we suppress this? Now we can think about it that way. We're just going to say, okay, there's like a true gold label for what the subject is. And we're going to just say we don't want this to look like the true gold label for any head. So we're just suppressing the maximum weight that's placed on the actual syntactic relations. And when we do that, as you can see, it's kind of like actually doing okay at the very beginning. Well, it's like it throws things off, and then it's so the thing that is bad at smaller scales is the syntactic attention structure itself. So actually suppressing it helps, which is interesting, as in this blue line is what happens when you suppress it, right? But then eventually you hit your big syntactic attention structure phase transition, and now you're no longer beating it by suppressing that. But the fact that there is this period of time where you can start beating it means that there are multiple viable representations that you can use to solve the overall sort of aggregate loss task, even if it's not going to help you with specialized linguistic phenomena. So we see there's this point where it comes together, and then we would say this is where like an alternative strategy maybe develops, even without access to this structure. So that's another sort of case in this list, yeah? Oh yeah, the BLIMP score is, I don't have that slide over here, but the BLIMP score never goes through that little, yeah, that's an important one. So we do confirm then that even though you get to go through this nice phase transition, you never go through the BLIMP phase transition. So you never pick up on these specialized capabilities. So, okay. So then this is an example where you have competition between possible solutions, right? So that's nice. Now I'm gonna go through some unpublished work. So you have to be nice. No, this is new results. So this is going to be actually in the autoregressive setting, a causal language model. And we're going to be talking about hierarchical generalization and this like hierarchical structure that's latent within the actual model. So there's existing results which show that language models, at least transformer language models specifically, don't necessarily learn hierarchical structure very easily, at least. Testing them with a few different sort of cases, but in this case, we're going to focus on question formation in English. The results I show are actually going to apply in other settings, but we're just going to focus on question formation. So English has a question formation rule, and the question is, and when you form a question, you can look in these ambiguous settings. Well, so it's either you're going to move the sort of closest verb like this. Yeah. What? Oh, I thought someone was saying something. So you're either going to move this like last verb over to the front to make the question, or you're going to choose based on the actual based on the like what is the sort of dominant auxiliary verb over here. So in this case, this makes clear why these rules are different, right? My unicorn who doesn't sing does move. So if you just go and like go for this first one, the one that's close to the subject, you can just say, okay, doesn't is going to move to the front. It's right over there near the subject. But if you instead say actually does is the dominant auxiliary higher up in the tree, then you move that over instead. That's like, because that's modifying this verb. That's the like root verb, right? So then the idea is that within distribution, you don't have any examples that actually clarify whether you're using the tree structure or you're just going based on position, like a linear rule. And you also get some examples of just basically a language modeling task that's actually just a copy task where you say, okay, just copy the declaration. And then the main task you're actually interested in is like, okay, now turn it into a question. Yeah? So there's this recent work finding that actually, even though originally it didn't look like transformer models were picking up on this hierarchical structure in this setting, that if you keep on training them with a language model, eventually it goes, wait a minute, everything's hierarchical. I should be using hierarchical rules, yeah?
just unstructured text, or is this on these particular sorts of input outputs, the entire thing you're training it on?
Yeah, it's everything. Every example is one of these two sort of formats. Either you're saying copy over the declaration. So it's like an emphatic language modeling task because it's also copying, really, right? So you either are copying the declaration directly, or you are copying, or you're like taking it and turning it into a question when you generate it, right? So eventually you hit a point where you start acting more hierarchical. Yeah.
Also to clarify further, is it that in the training set, they restrict it to cases where both of these rules would produce the same question?
In the training set. Oh, the training set. So what's out of distribution is any kind of is any case where there's a difference between the like judgment that you would use based on position with respect to the subject, or the like actual where you are in the tree. And I will show some examples of what that kind of sentence looks like, but I'm just going to call this compositional again. We can talk about it later if we have time. And it turns out, just to start thinking about this, it does turn out that you need deeper syntactic trees, or with like more with like deeper sort of like relative clauses in order to actually learn this. So if you only ever see depth 1 trees in your declaration examples, then you're never really going to learn like this good rule, right? And you also can't really consistently learn the nice rule when you're looking at depth 2, but you're pretty good at learning the hierarchical rule. And this is across random seeds. The only thing varying here is random seeds. You're mostly going to learn this hierarchical rule if you're exposed to the depth 3 declarations. Now, why is it that there's so much variance when you're specifically looking at depth 2? I mean, it ends up looking a little bit like what?
So is it depth of like relative clause sector embedding?
It's only the relative clauses, yeah. This is not like the entire syntax tree. This is only counting relative clauses as constituents and treating them. Yeah. So when you look at that depth 2, it kind of looks like the extremely high variance behavior that you get when you start mixing depths together. So there's something that is disambiguated in depth 3 and depth 1 that is not disambiguated in depth 2, or rather there's something mixed together in depth 2 is what I hope that you'll see in this. So the reason why that happens is that in this particular setting, your depth 2 trees are that they can take 2 different like possible forms, one of which is you get a relative clause that just attaches to the like previous relative clause and you can just keep going forward. And the other is that you actually attach multiple relative clauses to the subject itself, which is where you start having to actually represent hierarchical structure. Because if everything is just branching, boom, 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 then your scope only sort of moves forward, which that's not something that you need hierarchical structure to represent at all. So if you actually take the forward scope and the mixed scoping subsets and look at them separately, you can see mixed scoping behavior actually is where you get the hierarchical generalization pretty consistently. And if you don't have that, then yeah, it's not going to learn to represent this hierarchically. So then this is also a case where the emergence or actually in this case, grokking, or they'll call it grokking, the training phase transition, where you eventually go into hierarchical generalization, is actually a result of having access to multiple possible solutions that compete with each other. And to move into multimodality, I think we need to look at how stabilization, what?
There.
Yeah.
Is this after a certain amount of training, like
Yeah.
CAP training, would they all eventually, for the general depth 2 case, would it eventually, all these seeds eventually learn?
That is possible, but I'm going to talk. I mean, so for one thing, we have like learning rate decay, which means that you're not actually going to like they'll stabilize right where they are pretty much if you keep the same schedule, obviously, because you decay to zero. So, but if you don't think about learning rate decay, that's exactly what I'm about to talk about. I mean, it's possible that you would, because only the models that sort of commit to a specific simple rule actually stabilize in their out of distribution behavior. So this blue one is committing to a hierarchical rule. This beige one is oscillating back and forth, right? So they have very different total variation. And if you look at the total variation of each training run, you can see that this multimodal behavior that sort of polarizes the rules learned happens completely within the range of like actually stable training runs. And anything that's not like basically at one rule or the other rule is, you can sort of attribute it potentially to just that it's oscillating wildly. Yeah.
So are the blue and beige, are they just like different random seeds, or like is there
Just different random seeds? Everything here is about random seeds right now. So then this brings me into the multimodality thing. Different random seeds can bring you to potentially different, the only difference here is like how much sort of hierarchical suggesting data versus linear suggesting data you're giving. By the way, these are all different only in that respect. But the multimodality then. Multimodality is something that you get out of these competing solutions in this case. And it's because training runs only stabilize when they find one of those solutions and sort of commit to it. So now that we've talked for a minute about multimodality, I'm just going to show some more very new results that we're excited about. And this one is getting out of the natural language space. Just wanted to acknowledge that so that you don't say, hey, you didn't show us only natural language. This is about length generalization. Aaron talked about length generalization, so I'm not gonna talk too long. Basically, we train on up to 30 characters and then test on up to 100 various ranges. And this says 200. It's actually 250 seeds for every single one of these architectures and hyperparameter settings. And we're doing a counting task. We say, okay, start here, end here, and then see if it's able to actually pick up on the start and end. So this is a pretty classic form of compositionality, length generalization. It's pretty standard to call that compositional. We can talk about compositionality at the end of this. And look, it's emergent. Look at all of these emergent lines, right? Except that it also can look completely linear, super normal. It does not have emergence with every seed. So emergence is not about suddenly reaching the capacity required to learn. It also is about a shift in probability of breakthrough. So this is another bimodal sort of distribution. So these are the models that are able to length generalize. These are models that can't length generalize even a little bit, completely fail. So you can see this is multimodal, right? And you might go, okay, well, emergence is a thing that is unlocked magically at a specific scale. Or you might say emergence is a thing that where maybe there's a probability, but the probability is something that just responds to parameter growth broadly. Anytime you increase the size of the model, then the your scaling law responds in some way. So in practice, increasing depth and increasing width both change they both lead to increases in the average performance of a model across these 250 seeds. But they don't have the same exact effect. If you look at increases in width, you can see that actually there's certainly not an increase in the probability of a breakthrough. In fact, it looks like pretty heavy down at the bottom over here, right? Whereas it's pretty clear that increasing depth like this does increase the probability of a sudden breakthrough. So as in, it moves everything to the top like this. So you can have the same exact parameter size, but as you move all of your size from width to depth, you increase the probability of emergence happening pretty dramatically as you move. So how does width actually help? It's not increasing the probability of a successful run. In fact, if you look at this, it actually decreases the probability that you end up above like a 20% accuracy, which is the threshold we're sort of arbitrarily using here. And instead, all it does is increase the expected performance of a successful run. Okay, so, yeah?
Increasing the likelihood of a successful run.
Yeah.
Is that because like there are more like modes in what you were saying, like in the deeper model?
More modes.
Like more optimal. Like,
yes. Right. So so this is like a little bit mysterious because it's like because the simple sort of explanations you might come up with are sort of in conflict with the actual behavior here. But certainly it seems that if you think of this as like that there is a circuit that is, you know, somehow concealed there, that's obviously, and okay, to be clear, right. So you can see that there is 0% probability of a breakthrough at one layer model. This requires 2 layers. So like that the increase in the probability of like actually being able to do this increases with layers in a particular sort of pattern that's longish, you know? And meanwhile, and this is also sort of a conjecture possibly in terms of why, let me see, in terms of why why increasing your width actually damages your likelihood of a breakthrough, at least in this range. It's possible that increasing width just makes your unsuccessful runs too good. That you have like a little lottery ticket effect that improves the like fail runs by whatever like sort of a like complexity metric is appealing, let's say, too much for the model to sort of make the jump to learning a general compositional function, right? Okay. Any other questions? Okay. So so I'm going to recap, but then we have a little time. So I'm going to talk a little bit more about the syntax acquisition stuff from the very start. Okay, so we did see that mass language models have these specialized syntactic heads that develop very abruptly and are associated with a big drop in loss, and then immediately followed by the emergence of specific linguistic capabilities. And that when you train causal language models, the way that they develop a preference for hierarchical rules that reflect more of the structure of language is by being exposed to like mixed scoping, which actually requires hierarchical modeling. And that in fact, having more data in this case actually does make your performance worse. If that data is forward scoping, which is, I would say, pretty interesting. To go back over here, it's this is relevant if you were at the panel yesterday. That in this case, if you add more data, it actually, for instance, if you're at depth 3 and then you add depth 1 data, then it actually makes your out of distribution performance worse in the sense that it makes you less likely to learn a hierarchical rule. Yeah, even though, to be clear, both depth 1 and depth 3 are compatible with the hierarchical rule. It's just too efficient to represent the depth 1 data without it. Okay. Yeah, we've got, okay, so just to come back to it, I kind of think these 3 things are the same, but because when it comes to compositional representations, what you're really thinking about is a latent representational space where manipulations or changes have a like a systematic effect on the outputs that's determined more in that latent structure. And that sort of automatically leads to competition between solutions, because you could either rely on that latent structure, or you could find another way of representing things that doesn't have the same sort of behavior. And I think in general, this often does lead to extreme variation in behavior, because you have 2 possible rules. Although only obviously when you're sort of either looking at the training regime, like the actual effective training itself and timing, or if you're sort of, and you're sort of at a threshold of possibility in terms of both solutions being viable. I have other examples of multimodal behaviors. Yeah.
Necessary for a breakthrough. Breakthrough just defined in terms of pattern.
I think that there is no breakthrough unless it's like a really artificial thresholding effect, I would say. I think there is no breakthrough where you go from like this capacity to that capacity and magically you've completely guaranteed immediately. Like, I mean, that's maybe a strong statement, but just based on the probabilities that we see, I think that it is at least like hard maybe to find cases where there's, I mean, obviously this is like like parameter size is discrete. So maybe there's a case where you go from here to there and you're basically at close to 100% probability of a breakthrough. But I think it's likely that there are smoother patterns in terms of the emergence being actually expressed as like a probabilistic law that's very continuous, rather than by an abrupt 0%, 100% in terms of finding like a good straight edge representation. Yeah. So in the other, the syntactic attention structure stuff, another thing that we did find, since I have a little time, is that both of those representations were viable, like I said, in terms of early in training. So you do find this like sort of competing representation. But if you want to say, okay, well, in terms of the law surface, in terms of the like process of optimization, is there like path dependence here? Can you just actually get back to this other representation that's actually better at scale? And what's interesting is if you start out with your regularizer that suppresses this structure, and then you stop suppressing it, that generally, as you might expect, the longer you suppress it, the less you're able to recover this original structure, right? And also, like, the timing of it obviously is delayed when it is recovered, when there is that phase transition. And also, like if you suppress past that alternative phase transition that I showed, you never get like a second chance, a second transition. You never get that second breakthrough. So you can't just like do this big transition back. But it never really recovers, but the grammatical capability still is able to get picked up. So this alternative representation that you learn is still usable later on once you allow it to attend to modifiers. So there is this alternative strategy. And also, actually, if you briefly suppress that structure, you end up with better performance in terms of the loss. So actually, like, preventing the model from sort of like, this is sort of a simplicity bias case, preventing the model from actually finding that simplistic structure eventually lets you outperform the original model in some other basin. Anyway, okay. Does anyone have any other questions? Actually, I'll just, since we have a couple minutes. Yeah.
In general, in these phase transitions, did you notice like a pattern in the way the gradients change? Like, is there magnitudes explode?
Yeah, yeah, intrinsically, like when you hit one of these phase transitions, generally your gradient magnitude gets really big, and also you develop like a bunch of little outliers in the Hessian. So not only are you following a pretty sharp gradient, but also there's like, as you might expect, there's like multiple competing sort of directions to follow.
Gotcha.
Wait, so just so I'm understanding this correctly, you suppress the SAS structure.
Yeah.
You stop suppressing it.
Yeah.
If you stop using it late enough, it doesn't gain the SAS structure, but it does gain the ability to solve them.
Yes.
Even though all you changed was whether you're suppressing the SAS structure.
Yes.
So what, do you have any hypothesis for what it is doing?
Well, by suppressing the SAS structure, we're also, so anything that is a modifier is also going to be pretty close to the target token. So you're also preventing it from relying heavily on like nearby tokens. We have some sort of like, we don't have a lot of confidence in like what this alternative strategy that's like repurposed later is. But we do see that like that you get like a better, that you're able to use like long range context faster, sort of like you go from out to in, which is very different from how you normally would learn to model language, since nearby tokens are generally more important. So it's like it does more sort of topic modeling and less sort of and less sort of like local n-gram modeling.
Tried suppressing just attending locally.
Yeah, at some point we did that. It was, look, this was like a paper that's 5 papers. So there was some stuff that did not make it in to the paper that had 16 appendices already. Yeah. Okay.
You always like the speaker again.
That's too-